Okay, welcome. We're now having our press conference about science from Juno's Earth flyby, and we have three speakers who will speak in the order that I'll give you their names. Scott Bolton, Juno Principal Investigator with the Southwest Research Institute in San Antonio, Texas. John Joergensen, Juno Star Camera Team Lead with the Danish Technical University in Copenhagen, Denmark. And Bill Kurth, co-investigator for Juno Waves Investigation at the University of Iowa, Iowa City.
Good morning. I'm Scott Bolton, Juno PI, and we're here to talk about the results from our flyby of the Earth. You can go to the first slide. Juno flew by the Earth on October 9th. We launched from Kennedy Space Center in August of 2011, and we're going to Jupiter, and when we get to Jupiter, we'll go into orbit around Jupiter for a little over a year to study Jupiter's origin and formation and how planets are formed, how Jupiter formed, how planets are formed in our solar system, and how planets form in other solar systems as well. We also will study Jupiter's interior atmosphere and its polar magnetosphere. So this plot shows our trajectory. When we launched in August of 2011, when you launch from the Earth, you leave the Earth, but you're actually in orbit around the Sun once you've left the Earth. And the energy that you leave the Earth from dictates how far away from the Sun you can get. And so we left with just enough energy to get out into the asteroid belt, because Juno is a pretty massive spacecraft because we have to be able to tolerate Jupiter's radiation environment when we get there. So we're pretty massive and heavy, so it's hard to get us launched all the way to Jupiter just from the first rocket. So what we did was we launched and we went around the Sun and got all the way out to about the asteroid belt, and you can see that where that deep space maneuver is about as far out as we got. And then the Sun's gravity pulls us back in, and we use this technique in order to get more energy when we fly by the Earth. We fly by very close on October 9th, and we exchange some energy with the Earth, basically, and that's what the Earth flyby was all about. We exchange a little bit of energy. We get some energy from Earth, and we increase our speed and change our direction a little bit relative to the Sun, and that allows us to reach all the way out to Jupiter because we're now leaving the Earth with more energy than we came in with. Of course, the speed relative to the Earth stays the same, but all that matters is the speed relative to the Sun. So this plot kind of shows how that works, and on July 4th, 2016, we'll arrive at Jupiter and start our primary mission there. But we have some really interesting results at the Earth flyby, and we wanted to share that with you. And the Earth flyby was used primarily to test out our instruments and calibrate, but because we were flying by really fast, and if you could show the next figure, you'll see our ground track. We come in, you can see from that arrow the direction that we're coming in, and we kind of make a U-turn over South America there. And then we fly over. Our closest approach is about 500-kilometer altitude, and we're flying right over South Africa. And then we go up further north, and you can see we curve out and go. So we come in very fast, and we leave very fast. And we come in very close. And so that afforded us an opportunity to take a look at the Earth's magnetosphere as a snapshot. And we just left a scientific session, which was called sort of a day in the life of Earth's magnetosphere, where our scientists collaborated with other scientists that had satellites around the Earth to take a quick look at what was out there. And we kind of flew by in just a few hours, and so we kind of got a very fast snapshot and saw the context of what the Earth's magnetosphere was like and what state it was in. We wanted this so we could test our instruments out, but we also wanted to get some science out of it. But we also had some opportunities to use our remote sensing instruments, and we'll show some of those. One is the plasma wave instrument, which measures also radio waves, and we have some cameras on board. And so I'm going to show some pictures of our camera, which we call Juno Cam, and then I'll briefly talk about the other two things that we're going to present today by my colleagues right after I'm done. So let me show you first the first picture of the Earth. So here's Juno Cam was coming in. It's a camera that works with the spin, the spacecraft is spinning, and so as it spins, it builds up an image across like line images. As we make a spin, we spin around every 2 minutes. And you see 3 images of the Earth. The middle one, I think, is a methane filter, and the other 2 are just combinations of color filters off of our camera. The interesting thing about Juno Cam and all the images that I'm going to show you is this camera is not actually a full science instrument. It was put on primarily for public engagement, outreach, and education. And so we don't have a lot of science requirements on this camera, but we also, as a team, couldn't imagine going all the way to Jupiter, and we go very, very close to Jupiter when we arrive there. We're only 5,000 kilometers above Jupiter, and we go right over its poles. Nobody's ever seen what Jupiter's poles look like. And so we wanted to have a camera on there so that we could all see what Jupiter's poles look like and appreciate that. So what we do with these images, because we don't have a full science team associated with it, is we take that raw data and we immediately just pump it out to the public through websites. And we rely on the public, actually, to go in and process the images. And that's what you're going to see, is these images were all made by the public, people that go on to unmannedspaceflight.com or other places where we post these things, create pictures in their living rooms and at home on their computers, and then post them. And so we actually woke up the morning of the flyby and we were surprised that the first pictures were already made. We thought it would take longer. So the idea of putting them out to the public really works and engages them. And you'll see some beautiful. Let's go to the next ones. I'm just going to flip through these. This is a picture of the moon on our way in. And you can see it's about half lit just based on our geometry. Next picture. Here's a picture of the spacecraft. You can see we're solar powered, so we're the first solar powered spacecraft out to Jupiter. That's kind of newsworthy by itself. And at the end of one of the solar arrays is the magnetometer. It makes magnetic field measurements at Jupiter, and so it's put out really far away from the main spacecraft, so we're measuring the magnetic field of Jupiter when we get there. That's where some of the cameras are located. You'll see a little bit later today. But anyway, you have our high gain antenna that we transmit back to the ground is in the middle, and you see this picture of the Earth and the moon. This is made by the public. Again, you know, somebody in the public took this picture of Juno, added the Earth and added the moon from Juno onto the picture to make this. Next slide. Here's another picture of the Earth. These are all, again, made by the public. Next one. And here's an interesting shot that during the flyby of the Earth, we actually went behind the Earth in the shadow of the Earth, and it was the only time in the entire mission that we were going to go into eclipse, or the shadow, and we wouldn't be able to see the sun. Of course, we're solar powered, so we generally are pointing at the sun, and we need to point at the sun, but for a little while we were in the shadow. And we took this picture, and you could see the lights from Cape Town, South Africa, because it was right near our closest approach. So this is certainly evidence that there's life down there, and it's emitting light. Next slide. And here we just happened to catch a picture of Jupiter, our destination. And so when we noticed that, by luck, we looked out and there was Jupiter, and that's, of course, where we're headed. Next slide. And here's another beautiful picture of the Earth. Our planet is really beautiful. That's one of the things I think we all know that, of course, from space station photos and shuttle. Next one. And here's where we're headed. Now, when we get to Jupiter, we're going to study the atmosphere. So one of the things we're going to look at is the reason that you see these beautiful zones and belts. We don't really understand what's making those colors or whether Jupiter's rotating. These things are all moving in different directions and at different speeds, and we'll be able to study the interior and the atmosphere to understand that. We'll be looking at the polar magnetosphere. Jupiter's auroras are some of the strongest in the entire solar system. We are perfectly suited in our spacecraft science instruments and the orbit that we're doing to study Jupiter's aurora. And most importantly, we'll study the interior structure and the composition, which will help us understand how Jupiter formed. It's the largest of all the planets, and it must have formed first. And so it's helping us to understand how planets form initially when the solar system's getting created. So the sun first forms, and then somehow something happens that allows the planets to form. And that's really what Juno's about, is trying to understand that very first step in the early solar system that allowed the planets to form, and why they're different from each other, and why they're different from the sun. And this will shed light on not only how Jupiter formed, but how all the rest of the planets form, and how planets are forming around other star systems that we're now being able to see with our stronger telescopes. So what you're going to hear next is a couple of kind of interesting things that we were able to do when we flew by Earth. As we were approaching Earth, we also had a set of cameras that I showed you earlier that were on the outer part of the solar array. And these cameras are used in order for us to understand exactly where this magnetic field measurement is oriented. In other words, we want to know how the spacecraft is oriented or which direction it's facing very, very precisely so that we can map Jupiter's magnetic field. And so we have 4 cameras hanging out at the end of one of those solar arrays. And those cameras are special cameras. They're not like the ones in your phone or that you carry around your neck. These are cameras that are specifically designed to take pictures of faint stars, because we take pictures of the faint stars, and that's how we figure out which way we're pointed. So they're optimized for that. They're not necessarily optimized to take a picture of the Earth. But as luck would have it, we realized that on the way in, about 4 days out, these cameras had an incredible view of the Earth and Moon together. And so we took that opportunity to actually make a movie. And for the first time, humans will be able to see the Earth and the Moon in motion together, doing their cosmic dance. And so it's a very low resolution image because that's the kind of cameras those are. But nevertheless, the image is very profound because you're seeing the Earth sort of in its stage, in perspective with the rest of the universe. And you may recall years ago, Carl Sagan took an image that he called the pale blue dot and made a lot of important points about the fact that, you know, everything we know is on this little dot. All of history, it puts things into perspective. And I think our movie does the same thing, but with a moving image rather than just a still. Cassini also recently took a picture of the Earth that was, you may have seen, that was beautiful with Saturn in the background, in the foreground, and the Earth in the background. But again, it was just a still. But I think the points that Carl Sagan made are still relevant today and are applicable to the movie that we're going to be able to show you. And that is that everything we know is on this dot. This dot is a fragile piece of the universe. We like to think of ourselves as being very special because there is life here and we are intelligent and we're starting to explore. But in fact, we look the same from far away as all the other dots. And so that's a very important thing for us to realize, and we're all in it together. This is the, you know, everything you know, all the countries, all the people, all the history are in this dot that you see, and you're going to see this movie in a little while. And the point I want to make is that, you know, while we're all sitting there, all the different countries and all the different cities over thousands of years, and the different states have fought each other and they're going back and forth trying to get different things, the truth is we're all on the same team. And that's what this image really points out, is that we're all on the team, we're all on the Earth team. And so I think that philosophical perspective is sort of what Carl Sagan was pointing out, and I think it's still relevant. And I'd like you to keep that in mind when you see this movie. We also managed to, we worked and collaborate with a famous composer named Vangelis. He also worked with Carl Sagan and did the theme for the Cosmos series, and he also did some of the Tom Hanks themes and other themes, and Chariots of Fire may be the thing he's most famous for. He was very happy to work with us and saw the importance of this film and was composed some music to it, so you'll hear that. The next thing you're going to see is another experiment that we managed to do, which was a ham radio experiment. We had radio operators all across the Earth, all synchronize their signal to say hi to Juno. And so for the first time, I think, that I know of, the normal public, everyday public, were able to go in and hit their ham radio operator machines in such a way as to send a signal in Morse code that says hi. And here's this deep space spacecraft coming in from the asteroid belt on its way to Jupiter, and we managed to hear that. And so you'll see that data and hear it. So we've seen the first signal from Earth, from intelligent life sending out, reaching out. And the thing that's interesting is while all these ham radio operators, and it took thousands of them all across the world to work together in order to make this signal that we heard, that signal is actually sent out into space, into the rest of the universe. It's still traveling out there. Of course, as it gets further and further away, it gets weaker. But you hear about, of course, NASA and the military and many other countries have all communicated with satellites that are going by, but those are governments and organized and intended. Here is the public reaching out and being able to connect to a spacecraft. So with that, I'll let my colleagues take over.
Thank you, Scott, and good morning to you all. My name is Joergensen. I'm from Danish Technical University, north of Copenhagen. I'm going to tell you a little about the experiment we did, or training of our system as we flew by the Earth. Can I get the first slide, please? The camera, as you will see, is this big. It's the same size as a GoPro camera. The purpose is not to take high-resolution images of mundane things. The purpose is to look at faint stars, and it's updated. It's actually designed for this. The lens is faster than anything you can buy commercially, so it's really a low light camera. It has to be because Juno is a spinner. That means that it rotates about its axis every 30 seconds, and such a rotation speed will smear images violently if you're trying to look for faint objects like stars. Earth and Moon is, of course, what we were aiming at the Earth for this flyby. And while we were playing with the ideas of actually using the Moon for triangulation in a project that we are trying to do with NASA, trying to make a navigation method for going interstellar spaceflight, we actually learned, or just dawned to us, that the Earth was actually in the field of view as well, so we could get the chance of making a movie of this. Imagine you have to do a movie of a rotating spacecraft. Then you need to be rather snappy at the shutter and take an image every time your rotation is correct when the Earth happens to be in your field of view at the exact correct spot. And we had great help of the star tracker itself, because it knew exactly where it was pointing at any time. So we just asked this tracker to, every 5th rotation, take an image of the Earth-Moon system. And we approached from out 3.5 million kilometers out, or 2 million miles out, and that's actually what we're going to show you shortly. If I can get the next slide. Here's actually a small collage where you are this 3.5 million kilometers out, and you should be able to see the Moon as a very faint dot out here. The Earth itself is way brighter than the Moon is. Moon is dark as charcoal, and whereas Earth is rather shiny blue dot, as you see out here. And then you can see, as we approach, the Earth seems to be growing rapidly as we come closer. There's 240 minutes between each of these snapshots here. And you can see how the Moon starts to accelerate to the right in the image. You can also see, if you try to line up the Earth images you see here, you can actually see that we are not aiming for the center of the Earth with the spacecraft. We're actually aiming for the right edge of the Earth, as you see it here. And with that, you can see the big trick for a camera like this was really to tune it in a way that we were able to get images with a low light camera of a very bright object. And that was really the trick. The camera was designed for operating at the Jupiter system, where light is way more faint, 100 times fainter than what we are going to see in this movie. So if you can start the movie, please. This is a rendering of what we are going to see. You see the Moon to the left passing over the Earth itself, and you can see the speed of rotation of the spacecraft. The cameras are at the tip of the pointed boom at the one at the end of the solar panels. There will be 4 cameras. We only used one of the cameras for to take the images. And of course, this is a time-shortened sequence. Earth make 1 rotation per day, as you know. So you can imagine how fast it goes. Note the subsun point here. We came in with the sun behind us, so you basically have the light shining past us to the Earth system. You can see the stray light baffles here. They are meant to kill stray light from Jupiter once we're in orbit around Jupiter, so we can see the faint stars out there too. And here in the bottom you have the cameras. The cameras are shielded for the extreme harsh radiation environment, the harshest environment of radiation we have in the solar system out of Jupiter. So it's actually wrapped in pure gold. And here the movie comes. I hope you see there was the eclipse. The actual moon is actually moving across the Earth disk itself. It's quite beautiful. When you're seeing this, you're going to see 4 full rotation of the Earth. And it's kind of amazing to think that, I mean, this is all of humanity being scanned by the camera as we come in. And here it's enlarged. Try to look at the eclipse to the right here. You can see how small the moon is relative to Earth. It looks big when you look up. Here the camera is really fighting with the extreme strong light from the Earth. This is of course why you see the flicker. Nevertheless, we are 17,000 kilometers out when Earth moves out of our field of view. So, with this I give the floor to Kurth.
Okay, can we go to the next slide? Okay, so we just came from a scientific session where we talked about data from some of the other instruments on Juno and in the context of observations made from a number of other Earth-orbiting spacecraft. And I don't have time to go through all these observations and tell you what they mean and so on, so I'm just going to say that going from top to bottom, the top panel is the magnitude of the magnetic field. You can see where we came to closest approach, where it peaks out, and further out early in the plot. Time goes from left to right on this plot. You see fluctuations that tell us we're in different regimes. Some very sharp boundaries are seen there. In fact, there's we actually crossed the Earth's bow shock. This is the boundary between the solar wind and the gas around the magnetic bubble of the Earth. And we crossed into the bow shock. The pressure in the solar wind increased and pushed the bow shock back towards Earth, so we popped back out. And then about 10 minutes later, we crossed the shock again. And shortly after that, we crossed the magnetic boundary between the solar wind and the Earth again. And these same boundaries show up very clearly in the next panel. These are the plasma wave observations. This is the instrument that I'm responsible for. This represents frequency up to about 1 megahertz. The instrument actually measures up to 40 megahertz. And then we have 2 panels of energetic particle observations from the JEDI instrument, which these panels go up to about 1 million electron volts in intensity. These are electrons. These are protons. The high voltage for this instrument was shut down at this point in time as a means of protecting against very large count rates that were anticipated for the flyby. And over here you can see that these are radiation belt particles, and the plasma waves here are instrumental in modulating those energetic particles. The plasma waves can actually accelerate the particles, and they can also be responsible for scattering them into Earth's atmosphere, therefore losing them from the system. So we've had this is our first chance to actually get measurements from these instruments in a planetary magnetosphere, our first chance to see how they work in an environment that at least remotely resembles our target at Jupiter. So it was very gratifying for us to be able to take these observations. Let's see if we can go to the next slide. Now this is a still from the video I'm going to show you that has to do with this ham radio experiment that we did. And this is basically the same data I just showed you in the second panel with a different coloring scheme. White is bright and black is not. And this now goes up to higher frequencies, up to the 40 megahertz limit of the receiver. And I'd like to point out these emissions up here. These are terrestrial radio emissions, the terrestrial radio stations, shortwave stations, so on. And we can tell that because their frequencies are very steady, and they get stronger as we approach the Earth, and they get weaker as we leave This type of emission was detected on previous flybys by, for example, Cassini and Galileo. In fact, Carl Sagan, with my colleague Don Gurnett, wrote a paper on the Galileo observation saying, if this were an interplanetary spacecraft from another civilization, what could they tell from the observations Galileo made of Earth that there's actually life on Earth? And it was radio emissions like these that were argued that, okay, the fact that they're fixed frequency and so on suggests that they're radio stations on the planet, radio waves that are generated by intelligent life on Earth. We didn't actually demodulate, decode those signals on Galileo to determine what information content, if any, there was in those signals. So we thought, instead of doing exactly the same thing again, what can we do that would involve the public and also send a signal that we could actually decode from the Juno data? And so we came up with the idea of sending a Morse code signal, a very simple one, just the word hi, and we would enlist the support of ham radio operators across the globe. And we have evidence that at least 1,400 participated in this experiment. We devised a website that coordinated the result, people that coordinated the activity. The radio operators were assigned frequencies in the range from 28 to 28.5 megahertz. This is the 10-meter ham radio band if you're a ham. We devised a website that said key down now, key up. We slowed the message down. It actually took about 6 minutes to transmit this message hi. We decided that Morse code is made up of dots and dashes, and the word hi is 4 dots for the H, 2 dots for the I, and we decided to make those dots last for 30 seconds so that we didn't have to worry about the rotation of the spacecraft and the fact that our antennas would be rotating through the radio signal and making it difficult to interpret. So, and then we repeated the message every 10 minutes for 16 times. So we basically covered the span of a little bit more than a couple of hours centered on closest approach. And we didn't really know whether we'd be able to detect this signal at all. It depended on how many ham operators participated. It depended on the ionosphere, how many of these waves could actually escape, and so on. So this video that I'm going to show you is the result of this campaign, and the bottom line is, yes, we succeeded. We heard the people of the Earth say hi to us. After this video, I'm going to play a second video. We had so much fun putting together this campaign that in addition to this video that Dan Goods at the JPL put together, he also organized a very short, about a 4-minute documentary on how we did the campaign. And we all think that's kind of a fun thing to watch too. So let's start the first video now. And we'll have questions after the second video. The sounds you're hearing are a sonification of the natural radio emissions and plasma waves that we detected flying by Earth. So we've lowered these frequencies down into the audio frequency range so you could hear those. And that's what hi looks like in Morse code. Remember, each one of those dots took 30 seconds. There's a 30-second gap between each one. So this is what I like to call a sing-along with Mitch video. So at the top we had basically where we expected to see the dits, and the green squares are where we actually were able to pull the signal out of the noise. And we successfully detected a number of those messages and parts of others, and so we were quite gratified by that. Now if we can go to the next video.
Maybe it's something you can use, I don't know.
Juno experiment is something that a group of us came up with.
The biggest challenge we had was we didn't know if this was going to work or not.
If it works, you know, I'm part of history.
This is W6JPL Jet Propulsion Laboratory in Pasadena, California. Hello, CQ, CQ, CQ.
The Earth flyby is Juno's way of gaining some extra speed, changing direction so that its orbit can take it to Jupiter.
We said, what if we actually sent something to Juno? Basically came up with the idea that we could send Morse code to Juno, enlist the support of amateur radio operators around the world.
So the intent is to join amateur radio community together in a coordinated transmission from Earth to the Juno spacecraft as it flies by.
The website would tell them, okay, key down now, then key up, transmit for 30 seconds. And that's how we would send a DIT. Everybody knows Morse code is dit, 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 da, da. Well, it turns out to say hi to Juno, it takes 4 DITs, then space, and then 2 DITs for the I.
I thought, wow, that's a neat thing to do, and they're going to need a lot of people to pull this thing off. I said, I'm good to go.
We're getting ready right now. Here we go.
And now we are transmitting here.
They could hear ham radio operators all over the world doing this, which was really remarkable.
Everybody's doing this at the same time. Thousands and thousands of hams.
With any luck, the Juno spacecraft will be able to listen and hear all these amateur radio transmissions.
And so what we're doing now is we're looking at the data that's come down to see if we can put together that signal that says, hi.
Will it work? Who knows?
I have the audio from Juno. I'd love you to listen to it. Come on. This is it.
This sounds very cool.
Actually worked and it heard us.
When you think about what it is, it was really, really amazing.
How many times do you get to say hi to a spacecraft that's flying by your planet? To be a part of it, that was very great.
More than thinking about what it means to me, I think it's just such a great thing that humankind has the ability to think beyond our own environment. It's the curiosity, it's the adventuring spirit, I think, that the space program has given us.
Hi, Juno!
Hi, Juno.
Hi, Juno.
Hi, Juno!
Hi, Juno.
Hi, Juno. Goodbye. Thank you.
Okay, take 17.
I'd like to say that one of the guys that showed up in that video at a couple places was Don Kirshner. He's my lead engineer. He built the Juno instrument, the Waves instrument, and he also was one of the masterminds of putting together this campaign. He's also a ham radio operator.
Do we have questions?
Hello, I'm Harvey Leifert, freelance, K2HHV. And actually, my question is not about ham radio, at least not the first question. It's for Dr. Joergensen. I was wondering, you didn't say what the mission of this camera is. I mean, why are you taking pictures of faint stars when we have Hubble and other things out there?
Okay, no, the cameras are actually using the stars to find out what the orientation of the spacecraft is at any given time. You should think of a spacecraft that is moving through space at, in this case, some 12 kilometers per second relative to Earth, and rotating freely as it do so, will constantly need to know how it's oriented, and that's what the star trackers are doing. So these cameras are really small navigation cameras that is used to give the orientation of the instruments on board the spacecraft. The accuracy of those cameras are quite astonishing. They are used to give an accuracy in the pointing direction of what we term as 5 arcseconds, and that's about a 50,000th in clear measure. So that's way more accurate than you can do it with any mechanical system.
Yours isn't on, your mic.
Okay. Hi, I'm Irene Klotz with Reuters. For Dr. Kurth, I know you said you didn't have time to go through all the science, but and I understand that it was mostly just a test of the instruments, but of all those charts and things that you had up there, the graphics, is there anything that kind of popped out as unusual or that was unexpected during the Earth flyby?
I guess my initial reaction to that is no, I don't think we were surprised by anything. We were comparing measurements with a number of spacecraft, for example, the Van Allen probes that are studying the radiation belts. And so it was gratifying to us to see the energetic particles with the JEDI instrument associated with the radiation belts and the plasma waves associated that were measured by the WAVES instrument, because those two aspects have a very complicated interaction in the radiation belts. In fact, that's the whole purpose of the Van Allen probe's mission, is to understand that interaction. We found some interactions between the magnetic fields that Dr. Kernerney's magnetometer measured and the plasma waves, which was not a new phenomenon. It's the magnetic field has compressional motions in it in the region outside of the magnetosphere, but inside of the bow shock, which we call a mirror mode wave. And those interact with the plasmas in the magnetosheath to drive a phenomenon we call lion roars that are visible in the plasma wave data. It's a well-established fact, but to be able to go there with a new instrument, and a new set of instruments, and be able to measure that is of interest.
Hi, Molly Michelson from Science Today. Maybe you mentioned this and I missed it, but why does Juno rotate?
Juno spins twice a minute in order to, we use that as a way of stabilizing the spacecraft. There are two different kinds of spacecraft. You have something called 3-axis stabilized, and the other ones are spinners. We chose that, however, because it worked with our way of making measurements in an efficient and simple way when we got to Jupiter. So when we arrive at Jupiter and we're flying over it, we're spinning so that our instruments are able to see Jupiter and all share and take a turn seeing Jupiter, and then at the same time look back into deep, cold space away from Jupiter and essentially calibrate each time they do that. So it's worked into our science observation plan.
Other questions?
Well, since there's time, I'll ask one more about ham radio. I always understood that you weren't supposed to do that, just send signals out, that you're supposed to be making two-way communications and not just keying into the void.
Actually, we were sending a message to Juno. Each of the ham operators were required to identify themselves, as is normally the case. Let's see, I had another thought flip through my brain there. I think there is communication with Earth's satellites. The ham radio operators have flown satellites that act as repeaters. And this is, I agree, this is not exactly that same thing, but this was actually a way of coordinating activities with the ham radio operators. Each of the ones that participated have requested a QSL card, and we will send them a QSL card because we detected their signal.
Yeah, I'd like to add something, and that is that, you know, we had this experiment done, and the public basically transmitted and coordinated. They had to all work together. I mean, we all have to work together, and that's how we reach out and learn about ourselves and the universe. And this was a demonstration of people from all over the world doing that together. And it also demonstrated that here's a spacecraft that's traveling between the planets and going to another planet and coming by the Earth and had the ability to measure essentially intelligent life, a signal from intelligent life. And if you were to have that spacecraft go by another planet close enough and actually see something like that, a Morse code signal coming out that's clearly unnatural, it would be a very strong suggestion that that place had life. And so this was one of the first experiments that I know of where we had everyday people reaching out, and we demonstrated that here is a way of a spacecraft, a NASA spacecraft that visits other planets that is capable of detecting life. We haven't obviously seen that anywhere else.
Hi, Emily Lakdawala from the Planetary Society. The Star Tracker video is really cool. I'm wondering if you're going to be able to repeat that feat on approach to Jupiter.
We hope so. It should be a little easier. I don't expect that Jupiter and its moons will be quite as bright. You know, we had a lot of problems with the bright clouds of Earth as we approach because the camera is designed for faint objects. But it would be very interesting to be able to see a movie of Jupiter and its moons revolving around that planet. Nobody's ever seen that either. And it reflects back to Galileo's initial discovery. Oh my God, there's moons around this place, but we've never seen it in a movie form.
Actually, the mode we tested here at the Earth Flyby was just a dry run of what we are going to entertain while we are flying past the belts of and in through the tenuous rings of Jupiter, where we expect to find new moons. We're using exactly this technique, so we certainly will do this again. What we find, well, you have to wait a couple of years.
You have a question from the chat?
I do. I have a question from the chat. This question is from Michael Forster from Michigan Public Radio, is a science and technology editor there. He's wondering, this is a question for Bill. I'm sorry, I'm trying to read at the same time. Bill, do you have an estimate of the signal-to-noise ratio of the high message that was sent to Juno?
It was not very high. I would say it's on the order of a few dB. That's kind of a number that comes off the top of my head. The signal, first of all, we were challenged by the strength of the signal from the hams itself, and second of all, the noise level in the instrument. It turns out that, of course, sometimes it was stronger than others. When we were off the coast of South Africa is where we detected the strongest signal. Of course, we were presumably close to transmitters there and very close to closest approach at that point in time.
Thank you.
Any other questions from the floor? Any more from the chat? Okay, well, that wraps up this press conference. Thank you very, very much for your presentations, and thanks everyone for participating.